Summation notation. This is the symbols we use to stand for a sum. It helps us compress a long sum into a very short form. This symbol right here is a capital sigma. Sigma is a Greek letter. This is just a capital sigma, and it stands for sum. This I is an index, and what this says is I starts at 1, the index starts at 1, and it goes up to the number n. N will be a given number like 17 or 25 or 10 million. The a sub i's are called the terms, and what we do when we want to write out this sum is that we start with the index 1 and we write a1, and then we add on a2 and we add on a3, and then we keep on adding the terms on until we get up to n, and our last term is a sub n. These three dots stand for all of the missing terms that we didn't have space to write down between a3 and an. There may be a lot if n is large, or there may be just a few. Let's look at an example to see how this works. Let's see if we can write out the terms I equals 1 to 5 of I squared. What that means is that there's going to be 5 terms. So let's just not worry about the I squared for a minute, and let's look at I equals 1 to 5 and think about what that means. Well, that means we're going to have a term for I equals 1, I equals 2, I equals 3, I equals 4, and I equals 5. That's how this index works. When I equals 1, we just put 1 into this term, and we have 1 squared. That's the I equals 1 term. And then we add what happens when we put in I equals 2, that's 2 squared. And then we add what happens when we put in I equals 3 for I squared, and we get 3 squared. Then we substitute I equals 4 into I squared, and we get 4 squared. Then we substitute I equals 5, and we get 5 squared. And what we ended up with is a sum. And if you wanted to, you could figure this out and add it all together and get one final number. But the idea is that this is a compact notation for a fairly long sum like that. Let's look at another example. Sum I equals 1 to 4 of 2i over 5. Again, we start with the I equals 1 term, putting in I equals 1 into the term. We get 2 times 1 over 5, which is 2/5. Putting in I equals 2, we get 2 times 2 over 5, which is 4/5. Putting in I equals 3, 2 times 3 over 5 is 6/5. Putting in I equals 4, 2 times 4 over 5 is 8/5. So this sum, I equals 1 to 4 of 2i over 5, is whatever this number adds up to be. We don't need to add it up right now. The whole idea of this video is to try to understand how to write out summation notation. Let's look at another example. This one's a little trickier. Sum I equals 1 to 4, I equals 1 to 6 of 4. You might think it's just 4, but you'd be wrong. 4 is just the I equals 1 term. We have 6 terms. That is, we can't just use 1, 4. We have to have a term for each of the i's in this summation notation. So we need an I equals 2, I equals 3, I equals 4, I equals 5, and I equals 6 term. 4 stays the same. So when we put in 2, nothing changes. So we just add on another 4. When we put in 3, nothing changes. There's no I in here, so nothing changes. So we add on 4, add on 4, add on 4, and add on 4. And we get 4 times 6, or 24. That's the way the summation notation works going forward. Now let's think about going backwards. That is, suppose we had a big long sum and we wanted to compress it into summation notation. So here we have 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, 5 cubed, 6 cubed, and so on, all the way up to 19 cubed. And the instructions are to try to write it in this compact summation form. So this is going to be equal to, and we need a sum, and we need an index. So we're going to use I, and we can see that I is going to start at 1. The first thing here is 1. And there's going to be 19 terms, so we're going to go from 1 to 19. So we have the sum I equals 1 to 19. And then we just see the pattern. This is I equals 1. We have 1 cubed, I equals 2, 2 cubed, I equals 3, 3 cubed. In general, we have I cubed. This sum is a compact way of writing this down. Let's look at a little bit harder one, where we have to try to figure out how to compress this into a summation notation. Again, we can count the terms. 1, 2, 3, 4, 5. 5 terms, so we're going to have the sum I equals 1 to 5. But now we have to put in an expression, so we get 2, 4, 6, 8, 10. The way we do that is by experience. We had seen over here, if we have a 2i, if we started with a 2i, we get 2, 4, 6, 8. When we see 2, 4, 6, 8, that means we should use a 2i to represent it. In this case, the 2, 4, 6, 8 are in the denominator, so we use a 1 over 2i. and we go out to 5 so that our last term is 1/10. Anytime you see a sum in a forward direction, it gives you a pattern you can use in the backwards direction. So when you see I equals 1 to 5 of 2i plus 1 squared, if we write that out, 3 squared plus 5 squared plus 7 squared plus 9 squared plus 11 squared, you're seeing we get all the odd numbers. So that is, if you see odd numbers in a sum where you want to reverse, here we have odd numbers in the denominator, we can use the 2i plus 1 to capture that phenomenon. So here we have 4 terms, so it's going to be the sum I equals 1 to 4. We have even terms, 2, 4, 6, 8 in the numerator. So for that, we'll use a 2i. And then we have odd terms, 3, 5, 7, and 9 in the denominator. And we can see we can capture that with 2i plus 1. So we'll have a 2i plus 1 in the denominator. This is summation notation. It takes a little bit of getting used to, but it's very powerful because it gives us a way to very compactly write down a long sum of numbers.